Okay, so we're going to talk about 7.2, example 4, the middle of page 3 of the notes. So that's where you want to go. So here we have two curves again, right? Y equals root x and y equals x minus 2. Obviously, this one is y equals x minus 2. And this one is y equals root x. Now, how is the region defined? It's not just defined as the area between those two curves. It's actually defined as being bounded by the first quadrant and, of course, those two curves. So if I were to trace it in red, this is the region that we're considering. And I'll even shade it as well. So we want to find the area of that region. So here is the dilemma with this kind of problem. Is that the upper boundary is root x, right? But the lower boundary has 2. The x-axis, which is the same as y equals 0. Y equals 0, x-axis, same thing, right? As well as x minus 2. So it's not quite clear how to set this up, because the way we've set it up previously is you do upper minus lower, right? And then you take the limits of integration, the left's, x coordinate, the right x coordinate, and just integrate it. So what we're going to do as one technique, and we're going to do 3 techniques for this particular situation, we're going to divide into subregions. And here's how we'll do it. So I'll use blue. So we're going to break this into 2 regions. And actually, I'll shade one of them a little differently. So we have region 1 and region 2. And the reason I'm doing it that way is so it's clearly defined what's upper and lower. So for region 1, or area 1, it's pretty clear that I want to subtract root x from y equals 0. And what would you say the limits of integration would be for the first region? It starts at x equals 0 and goes up to what? A 2, right? So you can integrate from 0 to 2 of root x minus 0. Of course, root x minus 0 is just root x. So if you said root x, that's totally fine. But just to be consistent, we do upper minus lower, right? Upper minus lower. So we just want to integrate that. So if I do that, remember, root x is x to what power? 1/2, very good. So that's x to the 3/2 over 3/2. And when you have that, actually make sure I'm doing this right. Yeah, no, I'm doing this right. We're okay still. When you divide by a fraction, that multiply the reciprocal, right? So 2/3 times 2 raised to the 3/2 power. And don't worry about the 0 because it's just going to go away. So that's your first region, A1. And we'll hold on to that because we're going to add it to the second region, right? Now for the second region, A2, do a little separation there. We're integrating from what to what? Yeah, you can see it's from 2 to 4. Now in this case, it's going to be root x minus parentheses x minus 2. And you want to be a little bit compulsive with your parentheses because you need to make sure you distribute the minus correctly. And before I integrate it, it might help to kind of clean it up just a tad. That's x to the 1/2 power minus x plus 2 times dx. Okay. So let's scroll down. That's x to the 3/2 over 3/2 minus x squared over 2, doing the power rule, right? Plus 2x, right? Because as a constant, it's like 2 times x to the 0 power. So you add 1 to divide by 1. And of course from 2 to 4. So now we have to be really careful with how we do this. If I plug the 4 in, remember that's 2/3 times 4 raised to the 3/2 minus 8 plus 8. Remember, I'm just plugging 4 in, right? 4 squared is 16, divided by 2 is 8. 2 times 4 is also 8, but one's negative, one's positive. If I plug 2 in, I have 2/3 times 2 to the 3/2. Okay, I can't draw 3's. Minus 2 plus 4. And I think those cancel. So you wind up getting 2/3 times 4 raised to the 3/2 minus 2/3 times 2 raised to the 3/2. And of course, that's going to be, careful here, that's going to be minus 2. That's, of course, positive 2, but then you have a negative to the left of the parentheses. So we're going to want to combine. We're going to want to combine both these areas here. The first area, which is the yellow region, and the second one, which is the green region. So that's A1 in yellow, and that's A2 in green. Now, fortunately, when you add those two regions, when we do A1 plus A2, notice how these are just going to cancel out, right? Those are like terms. And can you evaluate 4 to the 3/2? What is it? Square 4, then cubed. So it'll be 2/3 times 8 minus 2, 16/3 minus 6/3, because 2 is 6/3. So you get 10/3. That's it. Yeah, it's a minus 2. So the area is 10/3. It was a little bit of work, obviously. I had to, think about, what are my boundaries, what's the top, lower, upper, and lower. I had to write 2 different integrals, and the second integral was a little time-consuming, a little labor-intensive.
Wait, so for the first section,
Yes.
you didn't have to subtract the equations?
It's y equals 0. Yeah, it's just root x. Right. It's basically find the area between root x and the x-axis, which really is subtracting 0, but who cares, right? Because just root x. Okay, that's one way you can do this. So we get, and by the way, you should get positive area, right? Because areas.
You're adding the two areas, right?
Right, because I broke it up.
But then, what are you plugging into that? Are you plugging in 0 and 4?
No, I did for the first region. I did 0 and 2,
Yeah.
and then for the second region, I did 4 and 2,
You just add those two.
and then I add those two areas right afterwards. Yeah, I'm not plugging anything afterwards. I'm just adding the stuff that's highlighted in yellow and green. But the thing is that the 2/3 times 2 to 3/2 cancels with the similar term in the other area. So now there's another way you can do this. It doesn't always work this way, but for this particular situation, it does. So using cunning geometry, or you could just say clever, or just being really smart with the geometry. This is our region again, right? The region looked like this. Kind of looks like a shark fin. So that was our region. Again, it was y equals root x. Y equals x minus 2. and of course, y equals 0, the x-axis. What if you did this? What if you just looked at root x with y equals 0, but then also looked at this right triangle here? If you subtracted a right triangle from y equals root x, wouldn't that get you what we're looking for? So basically, if you take what y equals root x is, which is, of course, if you integrate from 0 to 4 of root x times dx minus the area of the right triangle, you'll still get the same answer. So basically what you're doing is you're taking the region with just root x over here and pulling out that right triangle. It happened to work out very nicely. That would get us what we're looking for. Yes, go ahead.
On the test, would we be allowed to do either way?
Sure, if it works out that way. Yeah, so the question was on an exam, if this situation presented itself, I would be totally okay with that. Yeah, it may not always work though, just so you know, but in this case it does. And it's a little cleaner because this is, I think, a little easier to integrate. So that's, of course, we already know it's x to the 3/2 times 2/3 from 0 to 4. And of course, area of the right triangle is just going to be 2. If you plug in 4, you're doing 2/3 times 4 to the 3/2 minus 2. That's 2/3 times 8 minus 2, 16/3 minus 6/3. You still get 10/3. So it still works itself out. But again, it doesn't always work this way. But for this particular case, it does. So again, it may not always work this nicely. So now let me show you, I think, the preferred technique, the third technique. Usually that's what we do, right? We show you one that's kind of a little labor intensive, one's kind of cool, but may not always work out for you. The next one's a little tricky, but it is more efficient once you get it. But before we do that, we do need to do a little bit of a explanation of the theory behind this technique. So you guys can sort of just watch for now, and then I'll fill out the stuff in the bottom. There we go, perfect. Actually, okay. So I'm going to tell you what the third method is, just so you know what we're getting ourselves into here. You're going to rewrite, actually you do want to write this down. Rewrite each equation as x in terms of y. You want to rewrite each equation as x in terms of y. And integrate in terms of y. Now, just to recap some stuff we've done previously. Actually, it's wrong notes. Here we go. Okay, I thought these were completed. Never mind. I'll just draw it. Okay, so what we've done previously is that we'll have some sort of like, curves here, right? And we would draw these rectangles that were vertical. Or they kind of seem that they're vertical, right? And what we would do is we would add up the sum of all these, sum of all the areas of all these rectangles, where that's delta x, and the height was, of course, y upper minus y lower, which is why we did f of x minus g of x, right? Times delta x, and then we would integrate from a to b. We're reversing it here. Instead of stacking the rectangles from left to right, we're stacking the rectangles from bottom to top. So all these rectangles are going to have a height of delta y. And the widths is going to be x right minus x left. That's why we talked about that in the beginning of this section. I mean, if you just think about it, the area would be base times height. You could say your base is x right minus x left. So x right minus x left. And your height, of course, is delta y. And then you're just going to bunch them all up and add the areas. But the limits of integration also change too. They have to be in terms of y as well. Those are your limits of integration, c and d. So you don't do in terms of a and b on the x-axis, you do in terms of c and d on the y-axis. So everything's just kind of reversed. It's almost like taking these rectangles that we're used to seeing, which are vertical, and rotating 90 degrees, and it's like a line flat. And then you're stacking it from bottom to top. So the height of your rectangle is now delta y, and the width is basically x right minus x left. Or another way you could write it is f of y minus g of y. Because you're going to rewrite these equations so that x is in terms of y. So the sum of these rectangles, of course, as a sigma notation, is just going to be f of y minus g of y times delta y. Or as a definite integral, if you treat it like as a limiting case of number of rectangles being infinite and delta y going towards 0, you write it like this. Another parenthesis right there. There we go. So that's how you can do it. Okay. So let's do an example that deals with, then we'll do one more, and then we're done. Then it's time for March Madness. I didn't just say it on the video. Okay, right. Any score updates? No? No one's watching the games? Good. All right. Thomas Winnie's got an update for us. All right. Okay. Okay, we're going to do this one more time.
Learning's up by 5,
What's the score?
8-3.
That's early.
15.5 minutes left.
Only 3 points in first. Okay, see what Princeton can do. All right. Anyway, so here's how we're going to do this. Again, you're drawing these rectangles kind of like sideways or flat, where the heights are delta y. And we're going to call that curve is going to be x equals y plus 2. So basically I took this equation and I got x by itself. And then for the other equation, the one that's to the left, I'm going to call that x equals y squared. So that's my left, that's my right. But you had to rewrite them, right? As y, so as x in terms of y. Because consistently isn't one of the curves to the right of one of the other ones. Whereas doing upper lower, you have like 2 lower boundaries. So that's why it's better to kind of do it this way if you can. And our limits of integration will be from 0 to 2.
But let's say like there was some function where like when you doing it had like a function that went back down, and then you're doing it with this method, would you use the highest y value or the last y value as the end?
Wait, repeat that?
So like let's say one of them was like a negative x squared. So along with the interval, it peaked and came back down.
Okay.
And then you wanted to use this method, what would you use for the upper y limit? Would you use the highest y value in the interval or the last?
Should be the highest. Should always be the highest. Yeah. Yeah, always, yeah, it's basically, right. The lowest y value. So if you have something kind of like this, I think that's what you're trying to say.
Yeah.
And so you had something like that. But in this case, I just do the way we usually have done in a situation like this. Just, do in terms of x. But right, if you had a situation where, yeah, you basically just take the highest to lowest. Usually they're going to be they're going to intersect. That's what's going to happen. And hopefully you can see that too is the upper limit. I mean, you could always set the equations equal to each other as well. I should know better than that. Yeah, so, wait. Yeah, that's what x is, and then of course you can solve for y. But anyway, hopefully you can see it's 0 and 2 for limits. So now you just work it out. So that's y squared over 2 plus 2y minus y cubed over 3 from 0 to 2.
So why did you do that thing in the top right?
Where they intersect. Where x intersects, actually. What I probably should have done, actually, that was kind of stupid. So I'm trying to find the y limits. I should have just done y squared equals y plus 2. Because I already have x in terms of y. And if you do that, you would get 2 as one of the possibilities. So you get y minus 2 and y plus 1. So anyway, so then we plug in 2, you should get 4 over 2 plus 4 minus 8/3. You get 6 minus 8/3. That would be 10/3 again. So it's a little cleaner this way, if you can see the setup. if you just realize that, okay, we have a right curve minus a left curve, let's change this so it's x in terms of y. So we'll see this situation happen one more time in the next example. Any questions? All right, so one more. This one right here. Now it would help to sketch each of these graphs if you can. If you can't, you can use your calculator. You don't have to do it by hand if you don't want to. So if I were to graph this, I know it's y equals 4x minus 16. And of course, that's y squared equals 4x plus 4. So y is plus or minus root 4x plus 4. So you can always graph this in the calculator. 4x minus 16 is going to look kind of like this. I'm not going to graph the y-intercept because I don't think it's going to be necessary. Okay, that was a really terrible looking line. But, the other relationship is going to be a little tough if you're not quite sure what's happening. Maybe you guys might remember this from Algebra 2 Honors or regular Algebra 2 when you did conic sections. Maybe, I don't know. The vertex is at -1, 0. It's a sideways parabola. If I plug 0 in for x, I think y is 2 or -2. If I plug in, I think 3 for x, y is 4 or -4. And you try to find area enclosed by this. Can we get a score update, please? Good. 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 All right. So we got Princeton in my bracket. So anyway, so you want to find the area of that region. Now, it's hard to do top minus bottom, so we're going to do right minus left. What that means is that actually we should rewrite the equations. So I probably should have isolated x in each case. So 4x equals y plus 16. X equals y plus 16 over 4. And here, it actually will be y squared over 4 minus 1 equals x. I divide by 4 and subtract 1. If I want to isolate x. Or you could, keep the way it was originally. It could also be written this way as well. I guess you could move the forward and divide, y squared minus 4 over 4, same thing. So this is right here. And of course that's over here. And we need to find the limits of integration. What do you guys think the limits of integration are going to be? Yeah, it looks like it'll be from -4 to 5. If you're not entirely sure, you could solve for it by just setting these two expressions equal to each other. If you do that, I'll do the algebra off to the side here. If you were to set both those expressions equal to each other, you can multiply both sides by 4 to get them to cancel and move everything over to one side and factor y equals 5 or -4. So that's how you can get your limits of integration. Just a little bit of algebra there. So the integral is going to look like this, from -4 to 5 of the right curve minus the left curve. You could probably factor out a 1/4 because it is a constant for both those fractions. So it's y plus 16 minus y squared plus 4. You could probably go a bit further with that. Negative y squared plus y plus 20. Personally, I don't feel like integrating that, or I mean, I could integrate easily, but substituting 5 and negative 4 is going to get a little bit nasty. So I am actually okay if you were to use a calculator for this. You can see I already have it worked out for you guys. So if you, and the variable is arbitrary, it doesn't really matter. But if you have the right expression, and then of course we have to multiply by 1/4 or divide by 4, you would get 30.375 for your area. So it's 30.375. Okay, and that concludes the 7-2 notes.